So our main focus is our classes are based on mainly the mechanisms in organic chemistry. So last week we discussed about the concept of aromaticity. After that we discussed about some examples of resonance and hyperconjugation. We solved various problems based on that. Then we are discussing SN1 reaction. So following this chart, today we will discuss about SN2 reaction and others. So let's start. So what is SN2 reaction? In case of, if you recap the SN1 reaction is mainly substitution, nucleophilic substitution, first order reaction. What I told in that class, that in case of SN1 reaction, leaving group leave from the substrate first. After that, in the second step, nucleophile enters and we get our substituted product. But in case of SN2, both of the entering nucleophile and the leaving group eliminates from the system simultaneously. So, and why it is called bimolecular? Because in that case the reaction rate was not dependent on the nucleophile, because in the that was a stepwise process. I hope you guys have the, if I draw it. In case of SN1, the reaction was like, if suppose this is R and there is a leaving group, in case of SN1, the leaving group leave from the system first, generating a carbocation. After that, a nucleophile enters and we get our substituted product. So it was a stepwise process, and in that case the first step is the rate determining step. The first step is the rate determining step, and from kinetics we know whichever is the rate determining step, that determines the order of the reaction. The number of molecules participating in the rate determining step determines the order of the reaction. So in the rate determining step, how many substrates are involved? Only this one. So it is only one substrate is getting involved. That's why in case of SN1, that is a first order reaction. But in case of SN2, you can see this is our substrate. And the nucleophile attacks from this side and this leaving group removes. So and this is a single step process. Whenever something is written in this third bracket, that is called transition step. You can't isolate this compound. You can't get this compound in hand. It's a imaginary. We are imagining that this type of condition is happening. You can't get this compound in hand. Like you can't synthesize this type of pentacoordinated compound. This is a transition state. I think you know about the difference between transition state and intermediate. This is intermediate. This is carbocation intermediate. This is carbocation. If you guys have any doubt, you can ask, because I don't know if you have any doubt or anything I have to repeat, then you can tell me, then I will repeat that. This is a carbocation intermediate. is a carbocation intermediate, but this is a transition state. So what is the difference between intermediate and transition state? Carbocation intermediate can be trapped from the reaction. Like if you add something, you can trap this carbocation intermediate, or if you instead of nucleophile, if you are giving something, you can trap this carbocation. But this transition state cannot be trapped. You can't isolate this transition state. So that's why it is called transition state and it is called intermediate. This is the difference, that intermediate can be isolated but transition state can't be isolated. So in case of SN2, we get a transition state where this nucleophile enters and the living group leaves from the system, and this happens in a single step. This is a imaginary, so this is a actually this is happening in a this reaction is taking place through a single step, and in this step, so if a reaction is a single step, then that's the only step is available to determine the reaction rate of the reaction. So that is the RDS, that is the rate determining step. So this is the only step and it is the rate determining step. I'm extremely sorry because of this. I haven't received my pen yet, so once I hope within next week I will receive my pen. So then the pen I had is getting some problem, so that's why. So now this is single step and this is our rate determining step. And in this step you can see how many components are getting involved. This substrate and this nucleophile. So that's why there are two components are getting involved. So in this case, two components are getting involved. That's why it is called, the order of the reaction is 2. So it is a second order reaction. It is a bimolecular reaction. How many molecules are getting involved? 2. So it's a bimolecular reaction. The order of the reaction is 2. Whatever is written above is called the order of the reaction. Okay. So in this case, the nucleophile always, in case of SN2, nucleophile always attack from the back side of the living group. From the side while the living group is eliminating, the nucleophile always attack from the back side. Why? If you think from a molecular picture, you can see how this bond forms. It is forming through this overlapping between this fluorine and carbon. Now there is a huge electron density. Near a bond there will be electron density. There is a electron density. So if the nucleophile tries to come from this side, there will be an electronic repulsion between this. When the nucleophile is coming, the nucleophile also carries, here it is Br minus. So if it is negatively charged, so it also carries some electron density. So it is a ball of electron. It's a ball of electron. So here already there is electron density. So when it tries to come from a front side, there will be a huge repulsion. So it will hinder the attack of the nucleophile. It will hinder the attack of the nucleophile. That's why the nucleophile prefer to come from the back side. If we think that in a room we always lock the front side of the room, so if something is happening, it will be happening from the back side, because our backside portion is not that much electronically crowded. So this portion is not that much electronically crowded, and as the living group is removing from so the living group will go towards this pathway. So if the nucleophile also comes through this pathway, there will be huge electronic repulsion. That's why it comes from the backside always. So what we will know, that if it is SN2, there will be always a backside attack, and due to this backside attack, there is an inversion on configuration. That is called Walden inversion. What is called Walden? If you see, if it is asymmetric carbon, What is asymmetric carbon? We know that carbon can form 4 bonds. Carbon can form 4 bonds. If each of the 4 bonds are different, like it's forming 4 bonds with 4 different atoms. If it's forming 4 bonds with 4 different atom or molecule, then that carbon is called asymmetric carbon or chiral carbon. That carbon is called asymmetric carbon or chiral carbon. What I am saying, if the carbon is forming 4 bonds, carbon has 4 bonds, so the leaving group is already a different bond. So suppose leaving group is a bromine. Okay, so if it is a CH3, one is like ethyl, another will be like hydrogen. So this carbon has 4 different bonds. So this is asymmetric carbon. Now whenever any carbon is asymmetric or like that it has 4 different bonds, it will have a stereochemistry R or S. I don't know if I think it has been already taught in class 2 in school that if a carbon is asymmetric, that it has 4 different bonds, that carbon has a specific stereochemistry R or S. So I think you know about how to determine R or S. That is a different thing. If it is like this way, and then you can determine the stereochemistry of the compound. What will be the stereochemistry of this one? For just a trial purpose, not part of our subject in this chapter. If you read about stereochemistry, you will know that how to draw a Fisher projection from this flying wedge projection. So, or if you can determine from this position also. It is according to priority. It is 1, 2, 3, 4. So it will go from this to this side. So it will be R. Now, if a nucleophile attack to this position, the nucleophile will attack from this side and the nucleophile will go this position. So, if you see, nucleophile, if enters, will get, suppose nucleophile is OH. It's a hypothetical situation. Just think it's like this way. So it's coming from this side, So there will be an inversion. This total, suppose it's an umbrella. If the wind is coming from the side where you are holding the stick, its wind is coming from that side, then umbrella will be totally. It's also called the umbrella effect. Umbrella will be totally folded to the other side. So it will be like, suppose this is just going to this side. So it will be like, so what will be the stereochemistry of this compound? Similar way, this is 1, 2, 3, 4. This is hydrogen. This is anti-clockwise. The stereochemistry is so you can see the stereochemistry is totally reversed. The stereochemistry is totally inversed in this case of SN2. So there will be, if the carbon is asymmetric, the stereochemistry of the compound will be inverted. Like if it is R, it will be S. If it is S, it will be R. That's why this reaction is also stereospecific. What is called stereospecific? If you are taking a compound of a specific stereochemistry, like if you are taking your substrate with the R stereochemistry and you are performing the reaction, before getting the compound, or even when you get the compound, you know you will get 100% S. In this reaction you will get 100% S stereochemistry. In this reaction you will get 100% S stereochemistry. That is called stereospecific. And there is another term that is called stereoselective. That I will discuss after. But there is a difference between stereospecific and stereoselective. You always know SN2 reaction is a stereospecific reaction. What is stereospecific? You will get a selective stereochemistry from a selective stereochemistry of a substrate. So if you know the stereochemistry of the substrate, the product stereochemistry will be fixed. It will not vary. So that's why it is called a stereospecific reaction. In case of SN1, we knew that the rate of the reaction depends on the stability of the carbocation, because in that case the first step is the rate determining step, and forming the carbocation is the slowest step, that is the rate determining step. So if this carbocation is stable, the reaction will go forward in a faster rate. If this is stable, the reaction will try to go to that state, right? So this step for SN1 reaction is faster. So in case of SN1 reaction, the rate of the reaction dependent on the stability of the carbocation. But in case of SN2, there is no such formation of carbocation. So how the reaction rate depends? See, in this case, the nucleophile directly attacks to the carbon center. So as much the carbon center is less bulky, as much the carbon center is less crowded, it can take the attack. Suppose if some portion is crowded already, you can't go into that. If you go into a mall or something, that the gate which is more crowded, it will be difficult for you to enter, or in a train it will be difficult for you to enter. But if the door is less crowded, it will be easy for you to enter and to go into that mall or into the train. So that's why if the carbon center is less crowded, then it can attack very easily and remove the living group from the system. So that's why, you know, if the carbon is 1 degree, that means it has one carbon bond to itself. So here the carbon is 1 degree. Here the carbon is 1 degree. If it is 2 degree, the reaction rate will be slower. If it is 3 degree, reaction. So it is just reversed of the SN1 reaction. In case of SN1, the 3 degree is the highest because the carbocation stability is highest for 3 degree. But in case of SN2, the 1 degree is high because the bulkiness of the 1 degree is least. It can take the attack very smoothly. So this is the energy diagram. You can see this is our substrate, and in the transition state where the both of the nucleophile and living group is remaining at the same state, then the living group moves from the system and got our substituted product. You can see here the living group was this side, but here the nucleophile is totally inverted. The product has been totally inversion of the substrate. So if anyone asks you to draw the energy diagram for SN2 reaction, you can easily draw that. Here will be the substrate, here will be the product, and this is the transition state. In this position it will be the transition state. Now, depending on the condition of the reaction, in case of some reaction the starting material position will be up. In case of some reaction the starting material position will be down and product will be up. That is based on the reaction condition that we will discuss after some time on a problem. I think ma'am has already discussed about this in this week. So I have included one question based on that also. Okay, so this much is clear. So now you can, for SN2 reaction, so here I have provided two reactions. As I have already taught, SN2 is a very easy idea to guess that these two reactions will be based on SN2 reaction. So I just give it a shot. I will discuss it after. I will just give 5 seconds or 10 seconds. For both of them, 10 seconds. Just try. Here you can see this is epoxide. So obviously this is OMTBr, what is a kind of Grignard type of compound. So oxygen has a delta negative and magnesium has a delta positive charge. So if you consider that this is a nucleophile, this part is totally is a nucleophile. So if it is a nucleophile, it will attack one of the carbon center. It will attack one of the carbon center. So why it will be favorable? I am giving us hint that it will be go through a SN2 reaction. Because you can get an idea, there is no such formation of carbocation is not that much stable in this case because it is 2 degree, not 3 degree, and there is no formation of the living group is not removing totally from the system. You have to open a saturated compound, so it's not a totally carbocation is not generating in this step. Okay, so what will be the answer? Among these two centers, this is 1 degree. Why 1 degree? It has one bond with the carbon. It has one bond with carbon. So that's why it's 1 degree and this is 2 degree. This is 1 degree and this is 2 degree. So 1 degree is less crowded. And we know that rate of the SN2 reaction depends on the bulkiness of the compound or substrate. So this will attack this position and it will open. Now in the second step there is a H plus is given, so it will take one H plus. This will be our product. Okay. Now next is based on cyclohexane. So it is, if you just try to solve this on this structure, it may be wrong, because we know in case of cyclohexane, when this is above and below, there is a specific stereochemistry. So let's try to draw this. We know the stable form of cyclohexane is this chair form. So this is up. This is the stable form. If we just number it, 1. Okay. The another format is possible, which will be like this one. When this methyl is on the axial plus above and bromine is below equatorial. But we all know that any alkyl group on the equatorial position is always stable because it does not go through a synaxial interaction. Here this methyl undergoes a 1,3 synaxial interaction. The methyl group undergoes a synaxial interaction with this hydrogen. hydrogen. That's why this structure is stable than that of this structure. So reaction, you have to think about the reaction from this structure. If you start a reaction from this structure, you may get a different product, may get, I don't know, but you should start your reaction where the structure has the most stable structure, because in a reaction medium you can't control the structure of the reaction, right? It depends on the molecular arrangement, and molecule always try to get the orientation where it has the most stability. So if you think about the structure, so this Cn minus will come, so Cn minus will come from the above side, and this will get removed. So product will be Cn okay. We draw from this one, it will be like this. Okay. I hope it's clear. Let's go to our next problem. So which is the major organic product of the following reaction? Which is the major organic product of the following reaction? It already options are given, so just give it a try. Okay, let's try to solve it. It is also a Wigner type of compound, so this will be a delta negative. This is a delta positive. And we all know that aldehyde is a electrophilic center. That is the electron density is here, electron scarcity is here. So this will attack. And next step H plus is there, so it will attack and open, and next step H plus is there. So our product will be option B. See, you can have a mistake between this option A and B. Here you can see that there is a one carbon less, because it's attacking from the saturated carbon. It's coming from this carbon, so there will be a one carbon just adjacent to the aldehyde. So this will be, the correct answer will be B. Should be similar to that. Give it a try. This is a 1 degree carbon. So there will be SN2 reaction. This is negative. So just attack. Okay. Let's go to our next question. Which of the major product of the reaction sequence? Here what will be the major product of this reaction? Just try. I'll just give 2 seconds. It's simple. Here actually in that case the nucleophile already was given. This was the nucleophile which was attacking. But here you have to generate the nucleophile. OCH3 will not attack. See, you can see. Here already a OCH3 is there. So here you can see there is no double OCH3. So that means this OCH3 will not enter into the system. So you have to generate the OCH3 nucleophile here. Just try. So here this will give us OCH3 minus, which act as a base, which can act as a base. When there is no nucleophile is available, it can act as a nucleophile, but when there is another nucleophile is available, it usually acts as a base. Keep this anion, and this negative charge will attack here and remove the bromine from the system. So what will be our product? Option C. Not B, not A, because there is a 1 carbon less. Okay. Let's go to our next problem. So what I was talking about, the problem based on energy diagram. So which of the energy diagram represent an endothermic SN2 reaction? An endothermic SN2 reaction. So which of the diagram among these 4 will represent the endothermic SN2 reaction? I think Nandita ma'am has already taught you that what will be the energy diagram for endothermic reaction. So here this is the along this coordinate we determine the potential energy. The potential energy. So when a reaction is endothermic, that means the reaction takes some energy to get our desired product. So reaction will absorb some energy to go to the activation state and give us our desired product. So when this is happened, when this is our activation state where the transition, and we all know that in case of SN2 the reaction is a single step process, and in case of SN1 there is a double. So it is a single step process. The energy diagram will be a single hump. So the reaction, the option will be among option will be among B and C. A and D is already eliminated because they have asked for the energy diagram for SN2, not SN1. If it was SN1, then it will be a stepwise, then there will be double hump. If it is single step, it will be a single hump energy diagram. So our answer will be among these two. Now the question is, what is the energy diagram for endothermic reaction? Now in case of endothermic reaction, we need some energy to carry forward our reaction. So if you see, this is a transition state, and this amount of energy is required to our substrate to get activated and go to this activation state where the reaction will start, where the reaction can take place. And here it needs this much of activation energy. So from this one you can see the option B needs more activation energy than that of C. So more activation energy means heat here. So if a compound needs higher activation energy, that is higher amount of heat, that means it's the endothermic reaction. It's a endothermic reaction. So in this case, the activation energy is very less. Now you can see from other view also, if our product is in this case between substrate and product, the substrate is more stable because the energy is less. Whichever has less energy, that the stability will be higher. Like if a tree is moving too much, the stability will not be that much. Like the tree can fall down. But if the tree is still standing by, then that will be like the stability is higher. So that's why, because its energy is less. So whenever the energy is less, the stability will be higher. But here the energy is higher, so the stability will be low. So as the energy is higher, so to activate our substrate, we need some amount of energy and get our product. But when the activation energy is, we need less amount of activation energy, our substrate is already not that much stable. That means highly reactive. So it will react very fast and give us our product. And see, the product energy is very less than that of the substrate. So when we will get our product, a huge amount, this amount of energy, where it will go? This amount of energy will go outside of the system or in the universe, so it will get released from the system. So here, but here the product energy is this much. The product needs this much of energy, but we have to give the product energy is this much. From the activation state to get the product, this much energy is getting lost. But what about this much of energy, which we have to give excess to get our desired product? So our answer will be this one. So it's a endothermic, because we need an excess amount of energy, which is this much, excess amount of energy to give as our substrate to activate, to go to that activation state. But where in this case, sorry, one second. But where in this case, this much of this much of energy is getting released from the system. So that's why it is a exothermic reaction. This is a exothermic reaction. So our answer will be option B. It's not. Our option will be answer option B. Okay, I hope it's clear. When we need to give energy to the substrate to get to the activation state, then it is endothermic, because it's taking energy or taking heat. But when we get energy from the reaction, that is the exothermic reaction. So whenever the stability of the product is less than that of the substrate, that will be endothermic, because stability is higher than that of the substrate, then it will be endothermic. But when the stability of the reaction is stability of the product is higher than the substrate, then this amount of energy will get released from the system. That's why it will be an exothermic reaction. I hope it's clear. So they have asked to draw some possible mechanism for each of the following substitution reaction. In this class, we will just solve these two. These two you guys will try at home. Next week I will discuss. You can take a screenshot or a snapshot picture of this one. These two you guys try by yourself. I will try to solve this one for you. Just give it a try so that you can get an idea, because mechanism is such a thing. If you can't draw, if you don't draw by yourself, it will not get clear to you. By just reading things, you can't remember, because in every case the reaction is different. In every case situation will be different. But if you try to draw it by yourself, you will get an idea. And whenever you will get a similar kind of problem, then you can solve it. No one has solved all the problems of this world. People try to solve the similar kind of problems. If you like, I haven't solved this one before this class, but I have solved some type of problems like this one, which is helping me to get an idea how to solve this one. Okay. So let's start. So here, whenever the leaving group and the nucleophile are not at the same position, whenever the leaving group and the nucleophile are not at the same position for any saturated type of system, you can get an idea its reaction is going through SN1. Because otherwise, in case of SN2, the leaving group and nucleophile will enter and leave from the system simultaneously, so it will be at the same position. In case of saturated system. In case of unsaturated system, the situation is sometimes different. But in case of saturated system is this type of single bonded type of system. If the leaving group and the nucleophile are at the different position in substrate and product, respectively, you can get an idea that this reaction is going through a SN1 pathway. You can see, so here the leaving group is bromine at this carbon, whereas the nucleophile is at this position. So you can get an idea it's going through a SN1. So what will happen first? SN1, you just, whenever it is SN1, you have, when you see a problem, first, if it's a substitution, then you have to sort it out that it is a SN1 or SN2. When you get an idea, okay, this is a SN1, then first thing you have to do is remove the leaving group from the system. Then you will get this carbocation. Sorry, there is no. Okay. Now, what is the nature of this carbocation? How many carbon bonds are bonded to this center? This is a 2 degree. And this is bonded to 2 carbon. One is this one, another is this one. So this carbocation center is 2 degree. Less stable, not too much, but it's less stable than 3 degree. If it has any chance to transfer it to a 3 degree carbocation, it will always do that. So here there is an adjacent H. What we can do, we can just shift this H to this position. Then we will get our carbocation at this position. Because hydrogen has been shifted to this position. Now this is the nature of the carbocation is 3 degree. And Cl minus will attack and we get our desired product. Okay. I hope it's clear. It was very easy. I will solve this one and rest two you guys will try. So if it is now here also you can see the leaving group is at this position, whereas the nucleophile is this position. From that you can get an idea it's going through a SN1. is going through a SN1, because without forming a carbocation this is not possible. So when the iodine will remove, we will get a carbocation at this position, and the nature of the carbocation is 2 degree. Similar type of thing will happen. There is a hydrogen will be transferred. Okay. Then this OH2 minus H2O will attack, and we will get as oxygen is positively charged, so 1 H plus will be removed because it will become highly acidic, and we get our desired product. Okay, so these two you guys will try. It will be very easy, I hope. Just take a screenshot. Okay, let's go to our next problem. So next is, what is, now substitution is done. So what is elimination? An elimination reaction is a reaction in which atoms are removed as molecules or compounds. So elimination are generally catalyzed by a metal, an acid or a base. It often competes with the substitution reaction. Suppose in a substrate you are giving any base which may act as a nucleophile also. So if it is a base, it will perform elimination, but if it acts as a nucleophile, it will perform substitution. So sometimes it's competitive. So it's mainly used to get unsaturated compound from a saturated. What is saturation? What I was saying again and again. Saturation means there is no double bond. It's completely single bonded system. If you are a double bonded system, that is called unsaturated. Alkene, alkyne, double bond, triple bonded systems are called unsaturated system. So now the question is, when the reaction, when will you understand that if any substrate is given, what it will prefer, and any base is given, it will act as a base or as a nucleophile. The reaction will go through a substitution or elimination. The first thing you have to see that if it is a weak base, then it will undergo substitution, and if it is a strong base, it will undergo elimination. What does it mean? If it is like CH3, if it is like methanol, it is just a methanol, then that is weak. This weak base, it will undergo a substitution. But if it is a OMe minus, due to negative charge, it is highly strong base, and this type of strong base will undergo an elimination reaction. So from this one, if some reaction is given where you have given methanol, then first thing you will think about substitution, and if it is methanol OMe minus, you think about elimination. And of course, for elimination you need two components to be eliminated, that we will discuss. So if it is like this type of compound, if it's like this type of compound. There is no chance of elimination, right? There is no chance of elimination because there is no such hydrogen or any group is there to be eliminated. Here only one bromine is there. So here it will be just substitution. But when any substitute is given, when there is a possibility of elimination and substitution both, how can you determine? By the nature of the base. Now when the nucleophile is small, it can easily attack to the carbon center, but when nucleophile is bulky, it can't attack to the nucleophilic center. That's why whenever the nucleophile is small, it prefers the substitution. But when the nucleophile is bulky, it prefers the elimination. Suppose this type of substitute is there. Now you are adding OMe minus. It may undergo the substitution where it will attack here and this will remove from the system. But if you add a tertiary butoxide, it has a very huge structure. So it will be, if it tries to come to this carbon center to substitute, there will be huge electronic repulsion because of this, or electronic hindrance because of this here. So that's why instead of attacking here, it will just attack to this hydrogen and take up this hydrogen, and this bond will come here and bromine will be removed. Understood? Okay. So first, if it is weak base, then substitution. If it is small nucleophile, then it is substitution. Now high temperature always prefer elimination. This can be explained from this equation. From thermodynamics you have known that del G, as much del G is negative, the reaction is favorable. Now in case of elimination reaction, you can see for substitution reaction, in this type of reaction, from two substrate you are getting two substrate. Okay. So as we had the number of compound after and before the reaction is same, so we had the entropy change, that is delta is equal to 0, because there is no change of entropy, so delta is 0. But in case of elimination reaction, from one substrate we are getting two molecules. One is this one, or alkene, and another is our living group. So here the del is equal to 2 minus 1, so it is positive. So here the del S is positive as entropy is increasing. So when the del S is positive, when this del S is positive, this entire thing is negative. So as if it is positive, this, and if the temperature is also positive, then this entire thing will be negative. And to get del G negative, we should have this entire system highly negative to overcome the positive energy of, if it is to overcome the energy of this delete. So that's why in case of elimination reaction, if the T is higher, then this will be highly negative, and that's why if it is this part is huge negative, then the total del G can be negative. So that's why for elimination reaction, the reaction always favors at high temperature. The elimination reaction always favors at high temperature, because at this high temperature T will be high, so this total part will be negative, and it can overcome the del H value, and we can get our del G negative. We can get our del G negative. Okay. So whenever it's like room temperature, then it will usually prefers substitution. But if you are giving some amount of heat, it prefers elimination reaction. So there are two types of elimination. One is syn, another is anti. What is syn elimination? When these two group, these two eliminating group, that is this hydrogen and this bromine, these two eliminating group are the same side of this bond. If suppose this bromine is at this side, the same side of this bond, if the X and leaving group are the same side of this bond, then that is called syn elimination. That is called syn elimination. Here the eliminating group is this hydrogen and this amine. So it's eliminating from the same side of the bond. So it is a syn elimination. So there are different examples where I have taken the famous two examples, that is Hope elimination, where you can see this N oxide undergoes a elimination reaction and it eliminates the syn hydrogen, and it comes here and this eliminates from the system, and we get our alkene product. In another is Chuheb reaction, where this ester center is there and it will just, suppose this is like this, so it will take the hydrogen at the same side. Okay, so this will be our reaction. So these are called syn elimination. These are called syn elimination. So here is another problem based on syn elimination. Whenever there is a cyclohexane ring, always try to solve the cyclohexane problem by using the chair form. Otherwise it will be a mistake. It can be a mistake. So always prefer the chair form. Give it a shot. I will solve it for you. I just give 2 seconds just for you. It is not just, or think that what can be possible, because it's about mechanism. If you don't think by yourself, you can't attend an unknown problem. Okay, let's try to solve this one. So this is the anchoring group. It will go always at the equatorial. You count. This is also about. So now it's a seal elimination. So it will take a syn hydrogen, that is which is also up. If it is up, so it will take a up hydrogen. So it will, and here as already a methyl is in up, so it can't take methyl hydrogen from this position. So it will take hydrogen from this position and it will take the hydrogen. So our product will be double one at this position. Okay, I think it's very easy. Let's go to our next slide. So next is E2 is what is E1 elimination. So we just discussed about E2 elimination. So E1 elimination, you can correlate this E1 elimination with SN1. So where SN1, what in case of SN1, the leaving group removes from the system, the nucleophile enters. Similarly, in case of E1, the leaving group removed from the system, one leaving group removed from the system, then the hydrogen elimination takes place and we get our alkene product. So it's just similar to the SN1. So here you can see the leaving group removed from the system and this hydrogen eliminates and we get, so next is anti-elimination. What is anti-elimination? When both the leaving group are at the opposite position. The first example of anti-elimination is E1. So E1 is correlating with SN1. So you can see this leaving group removes from the system and generating a carbocation. Then the hydrogen removes and you get our alkene product. It's just the diagram is also similar to the SN1 reaction. So it's a unimolecular reaction because this first step is the rate determining step and the only single substrate which is getting involved in this step. So it is a first order reaction. Secondly, and the first step is the rate determining step, and you can all think about that it is a correlating with the SN1 reaction. If you see the rate law of the reaction, if you see the rate law of the reaction, you can see this only depend on the substrate. This only depend on the substrate. So this is a first order reaction. Next is what is E2 elimination. So E2 elimination is correlated with SN2. You have just learned about SN1, SN2. So just think E1 is like SN1 and E2 is like SN2. So E2 is a bimolecular reaction because both the group eliminating from the same step at the same step and at the same position, and as it is one single step, so this is the RDS, that is the rate determining step, as it is the single step process. So in this process, how many subcomponents are getting involved? Two, base and our substrate. So base and our substrate. So it's dependent on two components. So the order of the reaction is 2. So that's why it is called E2 elimination. That is a bimolecular reaction. If we see the energy diagram, it is similar to the SN2. It's similar to SN2 where the substrate is there and both the leaving group is eliminating from the substrate at the same time and give us our desired product, our desired alkene product. Okay. Let's solve some problems based on that. Let's solve some problems. So they have given this one, so it will be based on E1 and E2. So just give it a try, then I will solve it for you. Let's just give 2 seconds. So I hope E1 and E2 is clear. E1, where the living group leave from the system, generating a carbocation, then the hydrogen removes and giving us our alkene product. But in case of E2, the hydrogen and the living group eliminate from the system at simultaneously and giving us our desired alkene product. So here we need therefore, and specific thing about eco-elimination is I forgot to tell that for eliminating these two atoms, this living group and this hydrogen, it need a anti-periplanar arrangement. Anti-periplanar arrangement. That is, both of these eliminating group should be anti to each other. That's why I was talking about anti-elimination. Strictly, both of the eliminating group should be exactly anti to each other. That is exactly at the opposite direction. So here you can see getting a alkene. So from the product you can get an idea that elimination should be take place. Otherwise you can't get an alkene from a saturated compound. So you have to find the anti-periplanar H to eliminate this bromine. So now at this position there is no anti-H. There is an anti-bromine atom. Bromine can't be removed by this base. So here the only anti-H is available at this position. See, this is totally anti to itself, and here is another H. So there is a H here. So this is totally anti-periplanar to this bromine, and this hydrogen is anti-periplanar to this bromine. So this hydrogen will come here and bromine will be removed. Similarly, this hydrogen will get removed. We get our desired product. So for E2, a very important thing is the anti-periplanar arrangement of the two eliminating group. So it should be anti to each other. You always remember that. Now suppose these two hydrogen were marked. Somehow you have marked these two hydrogen. Now from this structure you can't know that which of the hydrogen is getting eliminated. But somehow if you have marked these two hydrogen, like you have replaced one of the hydrogen with a deuterium or something, then from that you can get an idea that which hydrogen is getting eliminated in the system. Suppose if you have deuterated this hydrogen, in the product you will not get any deuteration because this will get eliminated, right? If you deuterated this hydrogen, it will get eliminated, so it will not get any deuteration in the product. But if you deuterated specifically this hydrogen, you will get a deuteration in the product. From that you can get an idea which of the hydrogen atom getting eliminated. And here the scientist came up with an idea that for A2 elimination you always need an anti-periplanar arrangement. The next thing is classify the following carbocation from the least to most stable. So which of the carbocation is least to most stable? Carbocation stability we have discussed in the last class also. Just give it a try. Okay. So this carbocation is 1 degree. This is 3 degree plus benzylic. Benzylic means it has an adjacent benzene. Adjacent benzene. So it is at the benzylic position. The carbon just outside the benzene ring is called benzylic. So this is benzylic position. So it can be stabilized by the plus R effect of the ring. You can get some stability. This is 2 degree. This is 3 degree. This is also 1 degree or 0. Okay. So what will be? So here at least it has a plus R effect of 1 methyl group. It has plus R effect of 2 carbon atom. It has plus R effect of 3 alkyl bond. It has no such effect. It has 3 carbon so alkyl bond plus a plus R effect. So the least to most, the least stable. So here you can see. Then A. I don't think that. Then C. D. The correct answer, the highest stable would be most stable. It has 8 pi electron. It has 8 alpha hydrogen. So it has 8 hyperconjugative structure. So it has some greater stability. But both of them have 6 pi electron, 6 alpha hydrogen. So there will be 6 hyperconjugative structure. Now it has a resonating effect on oxygen because it has a unique as well as of benzylic. Whenever it is a benzylic carbocation, more hyperconjugative structure. This will not be correct answer. So we are just come to an end. Just 3 more problems. As it has more hyperconjugative structure, so it will be more stable. And as the hydrogens are 8, we are getting this alkyl product, the alpha hydrogen saturated product from a saturated system. So it will be a elimination reaction. So just give it a try. And how can you realize if it is a E1 or E2? The similar type of strategy for SN1, SN2. How can you get that if the 6 alpha hydrogen profile are not at the same position, you can get an idea that it will go through a SN1. Similarly, when the leaving group and the double bond are not at the same carbon, see, if it is a leaving group and the double bond should be at the same carbon, then that will be SN6 alpha hydrogen. Then it will be eliminated the same position and double bond should be it will have on the carbon hyperconjugative structure this side or this side, like this similar to this one. Conjugative structure, if it has more stability. So the highest stability is this A. Then both of them have 6 alpha hydrogens, so carbon have equal stability, but so it's having double bond. So 6 stability is given by the oxygen bond after the reaction. This is the leaving group carbon and the oxygen is double bond after the reaction. But oxygen after the reaction, the leaving group carbon center does not contain pi bond. So it has greater stability than B. So the get idea order will be A, C and B because it's going to a carbocation intermediate. Otherwise it won't just confused by the answer. It won't be possible. It will be the right answer will be A, C only A greater than C greater than carbon not contain the double bond. The answer is it will not be the answer. Because B has already 6 electrons, then there will be a shifting or 6 alpha hydrogen is possible, and A has 8 alpha hydrogen. So anyway, so B has to form that you can get an idea the reactionability than that of the A, because B has pathway. 8 alpha hydrogen. So just give it a more hyperconjugate structure. Our target will be to form the carbocation. So it has the stability, it has 8 alpha hydrogen, it has 6 alpha hydrogen with this pi bond resonance, it has 6 alpha hydrogen with this oxygen resonance. So as it has 8 alpha hydrogen, so it is more stable, and among these two, as oxygen lone pair giving probability is greater than this than that of this pi bond. So that's why C is more stable than that of B. C is more stable than that of B. So the stability order will be A, C, B. Okay. So let's go to our
Excuse me, ma'am.
yes.
Ma'am, I wanted to ask one thing. Does this mean that hyperconjugation provides more stability as compared to resonance if we are considering 8 alpha hydrogen and 6 alpha hydrogen here?
Because if there is alpha hydrogen is available as it is, then acid is there, so if it is some H plus, in case of resonance, if you are getting some aromaticity and all, that will be a different case. But if there is no aromaticity and all, but you are getting alpha hydrogen, hyperconjugation will have more effect, because there is a sigma bond which is getting delocalized. So it will give more importance to this structure to gaining stability. In this case, it is a good living group.
Okay, thank you, ma'am.
So let's go to our next topic. This is the last one. So the types of reaction mechanism. I think Nandita ma'am has already taught all these things. I am just giving a recap so that you can connect with the upcoming shift always. So there are 3 types of reaction. One is polar, radical, and concerted. The shifting always happen from the adjacent carbon. The positive and negative are reacting with carbocation. One will be electrophilic center, another will be nucleophilic center. One center is electron deficient and another center is electron efficient, and both of them will react. That is called polar. Another is radical. What is radical system? Radical means when two radical, like one electron get combined with each other. That is called radical. And concerted means it's happening in a single state. Of this hydrogen, another is elimination of no such formation of electrophile or nucleophile or any center is electron deficient center is not creating. It is just partially electron deficient, partially last week I have talked about hyperconjugation. They are not forming a proper double bond has cation or more number of alpha hydrogen. In a same system suppose highly stable. That alkene system is more stable. So next classes I will discuss about the concerted, which is concerted. If without this hydrogen eliminated, I will just drop both of the product. There is no formation of a solid positive or negative charge. There is a partial part you can, as the product is already drawn together, you know which hydrogen will be eliminated. But suppose if you have not, so there are different type of polar reaction. If the substitution, elimination, addition, this hydrogen is eliminated, we will get. So what is substitution? There are 2 types of substitution. One is nucleophilic, another is electrophilic. What is nucleophilic? If nucleophile is coming and substitute hydrogen one form a system, then that will become nucleophilic substitution. Because nucleophile is coming and substituting both of the possibility. And electrophilic substitution means which is when the electrophile is substituting some based on that. Suppose you have a base double bond has how many alpha hydrogen? If a nucleophile, if you have a benzene ring with any group or any functional group, if any nucleophile comes and substitute that one and insert into that benzene position, that will be so how many total 5 hydrogen. And suppose if a electrophile comes and insert into that benzene, that will be alpha hydrogen.
Number of alpha hydrogen represent the number of hyperconjugated structure, and
one is SN1, SN2,
number of
and there is
hyperconjugated
another
structure
type of
is higher,
SNI that is not that much
more
important.
stable. So there will be 5 hyperconjugated
SN1
structures.
and SN2.
But here
And
number of
electrophilic
alpha
substitution
hydrogen
are two
if you
types.
count,
One is aromatic electrophilic substitution, another is aliphatic electrophilic substitution. Is clear by the name. Aromatic will be in the aromatic system and aliphatic will be in the aliphatic system.
here it will be 2.
Next is elimination.
Three,
Elimination
three,
and
three,
two
three,
types.
6,
Syn elimination and
8,
anti-elimination. Syn
10.
elimination means
Number of alpha
when
hydrogen
the
is
eliminating
10. So
groups
that's why
are
it will
seen
have
to each other. Seen means both are in the same side
10
of the bond
hyperconjugated
and they are
structure.
eliminating.
So it will have
Suppose
10 hyperconjugated structures.
in
So
a
our
class,
desired
if two
product
students
will
are
be
living from a
always
same
this one.
side of the
If
class,
its product is
then
not
that is
given,
seen.
we will
If one
determine
student
the
is living
product.
from
Now
the one
we
side
know
and
the
another student is living
criteria
from the another
determine
side,
which
then
double
that
bond
will be an
will be
anti-elimination.
preferred.
So
You have to
anti-elimination are
eliminate
three types.
hydrogen from
One,
that
one
side,
CV and
but
T2.
after eliminating the hydrogen
All these
atom,
1 and 2
will
whatever
get
I have shown
the
is
most
represents
stable
the order
double
of the
bond.
reaction.
We will get
Order
the
of the reaction
most
we have
stable
read
double bond.
about the kinetic theory.
Next is this
You
one.
have know about the order of the reaction.
Just
Order
try.
means
I will give 2 seconds.
number of molecule or the number of substituent which affect the rate of the reaction. If one substituent affect the rate of the reaction, that will be first order reaction. If two substituents affect the rate of the reaction, that will be second order reaction. So in case of SN1, only one substituent affect the rate of the reaction, and in case of SN2, two substituents affect the rate of the reaction. Similarly in E1, one substituent E1CB also one, and in case of E2, there's two substituents affect the rate of the reaction. And there are another type of things
So
like
similar
addition,
to this one.
elimination and elimination. All these will be
First,
discussed in the upcoming classes. So
it
our
will take the proton.
today's goal is to explain what is substitution and mainly what is nucleophilic substitution. Here I am discussing what is nucleophilic substitution. When an electron-rich nucleophile selectively binds or attacks the positive or partially positively charged of an atom of group or atom and replace the leaving group, that is called nucleophilic substitution. As I have shown, it has two types, SN1 and SN2. This is SN1. This is SN1 and this is SN2. In case of SN1, this is a stepwise process where this leaving group removed from the system and a carbocation gets generated, and then the nucleophile enters and we get our desired compound.
If it has a chance
in case of SN2,
to get
the nucleophile attacks and the nucleophile removed from the system, and we get our desired compound. Understood? In case of why in
there will be a
this
bond shift.
case it is happening in a stepwise when the living group
Here
is leaving from the
initially
system.
in the last
And
problem
after
that
that
hydrogen
the
bond shifted,
nucleophile
and
is
here
entering. But
one,
in this
two,
case, both the
carbon bond
happening at
as there is no hydrogen available.
step.
There is no hydrogen available. So, it will
So
be
what
one,
is
two,
SN1
carbon,
reaction? So it's a unimolecular
bond shift.
stepwise. Carbocation generation is the rate determining step, and rate depends on stability of the carbocation.
Rearrangement
What I am
is
saying?
totally
This is a
based
stepwise
on
process.
how you are
The
practicing
first
the
one is
problem.
living group is
I don't
getting
know
removed
about
from
this
the
problem,
system and
but I
generating
have
this
solved this type
carbocation.
of problem earlier.
And then
So
the nucleophile
rearrangement
is
is done
entering
properly
and
based on
getting
idea.
this
There is
product.
no such
Now, between
hardened
these two steps, the
code,
first step is the
some
slow step, and
problem
according
while
to the
you
kinetic
did
theory, we know
can
whichever
answer or
is the
you
slow
look up
step
again and again.
is the
So
rate
rearrangement, how much,
whichever is
as
the
much
slow
as you
step
can
is
solve
the rate determining.
reaction,
Now,
solve problems, practice
the number
problems,
of components
previous year,
which are
whatever,
getting
wherever
involved
you can
in a
get
rate
anything,
determining step,
then
with that
it
defines
will give
the
you
rate
a
of the reaction,
idea
or that
how
get
rearrangement
involved in the
will take
rate
place.
law. You know about the rate law? If R equals to,
So this will shift and you will get
rate constant, now in case of SN1,
positive charge will be here.
you can see in this slow step
So there
only
is a hydrogen
this
available.
substrate
As there is no hydrogen available,
the
H
nucleophile is
is
not
already
getting
part of
involved
a
in the
alkene.
first step. So
There is
the
a hydrogen
rate
available.
law only depends on the
We get our
substrate.
desired product.
That's why it's called unimolecular or first order reaction. That is called a first order reaction because there is only one substituent in the order. So the order of the reaction is,
and last problem for today's class.
Order of the reaction is 1 because only one substituent which is involved. Because in this first step, in the slow step, the leaving group, the nucleophile is not involved in this step. So it only depends on the substrate and stability of the carbocation. Because in the slow step we are generating the carbocation. As much this carbocation is stable, this reaction will be faster, and if the slow step is faster, that means the rate of the reaction is fast. So the rate of the reaction will be higher. So the stability of the carbocation increases, the rate of the reaction increases. Because the main path, which is the slowest path, if that is faster, the slow step is faster, then the rate of the reaction will increase. Because this step is not considered for the rate of the reaction, only this step is getting considered. And if you can enhance the rate of this slow step anyhow, then you can enhance the rate of the reaction. That's why if the enhance the stability of the carbocation, you can get more stability rate of the reaction. So as we know, by the hyperconjugation and all, the 3 degree, that is the tertiary carbocations are more stable. That's why the rate depends on stability of the carbocation is not that much stable. Rate will be higher 2 degree, then
there is a
1
chance
degree.
of
Understood?
bond shift.
So there is another question which is from assignment. So the correct order of the given bromide for SN1 reaction. So SN1 means the leaving group will remove from the system. Leaving group will get removed from the system, and it will generate a carbocation. So whichever carbocation will be stable, that will be react in a highest rate.
Carbocation will be shifted
So
to this position.
So many of you has already solved.
Now as the position has a
Okay. So here, if we remove the bromide from the system,
hydrogen,
we will get,
so hydrogen can be shifted again.
how many pi
This one,
electrons?
as it is 2 degree,
2.
stable than this one, but not that much, because 5
this
member
one
is
will get-
stable, but not that much. So that's why
How many pi electrons?
okay. So this is 3 degree plus 5 member ring. So now a hydrogen will be eliminated. Now we have to see which hydrogen will be eliminated. There is two. These two positions are equivalent, so you are just considering one and this one. So if we eliminate from this position,
So you can see, this is a toponium ion, that is 6 pi electron, aromatic. So it will be always
or if this hydrogen is getting eliminated.
this will be aromatic.
Get this one. Now how many alpha hydrogen this have? 2. 2. So it will be 4. But here the number of alpha hydrogen is
Okay.
sorry.
So the highest rate will be 3. After that, it has 2 pi electron, it has 4 pi. As it reaches 4 pi, that will be anti-aromatic.
So
So
the
that
number
will
of alpha hydrogen is
least stable 2. So the least stable is 4,
6. Here the number of alpha hydrogen is
and it's not aromatic.
4 and 3 7.
But it has 2 pi electron.
See,
You
this
can
is the
consider
exception.
aromatic. It's not
In
aromatic
spite of
because there is a no. But if you can
having
consider just a
more
stability
number
of the
of alpha
carbocation,
hydrogen,
it has
we are
stability
getting
of this carbocation.
this one as
So
our
that's
major product.
stability order
This
will be
one.
like
Why? because here is a exocyclic double bond. Here this is a exocyclic double bond. 5-member ring has
Why we
this
are
type of
considering
structure.
this one as a first term? Because it is aromatic.
5-member ring present in the
Second,
medium.
this
You
one
just
why? This if we just consider this as a allylic
yeah,
system, just
3
allylic
type of
pattern.
structure.
Because this is not aromatic, there is a no
5-member ring stays
cyclic
like this.
conjugation.
So this
If we
type
just
of
consider it
5-member
as
ring
a allylic system, it has some
contains a double
stability.
bond here.
But in this case, the
Daily
carbocation is
angle
anti-aromatic.
stem create at
Formation
this
of an
position.
anti-aromatic
Because
system is
whenever
highly
this is
unstable.
an alkene system,
Will
the
not get formed.
angle
That is,
chain
you can't even
inside
this
this
carbocation will not generate
double
in the
bond
system.
should
The
be
rate is least means this carbocation will not generate. If you in a reaction vessel, if you give this one and add some
greater than that of
this center will not
case
even
of
generate.
5-member ring. So
Yeah.
there will be huge angle strain because the 5-member
That's why
tries to
this will be our
squeeze
state
the
of
ring,
reaction.
whereas this double bond tries to expand
it's
the ring.
clear.
So there will be a huge
So this is
ring
the last
strain at this
slide of
position.
our
Any double bond at the ring
it's almost like
exocyclic
this
double
an
bonds
extra
are
question.
not that much
Try to
stable.
solve.
That's
There's
why
no option. You
our
have to draw
desired
the
product will be
product.
this
You
one.
can't send me the product.
Okay,
But
so
whenever
let's try to
you are getting any product,
you have to consider the stability of the double bond and also
it will be
through hyperconjugation and also by
as
the
you
structure.
see,
If it is a
there's a
exocyclic
methanol
double bond and
bromide,
there
so
is a
bromide will get
competitive
removed from the
phase
system
difference
and
is not
carbocation
that
will
much
generate.
huge. In the last
After
problems
that
you
what
can
will
see
happen?
the alpha hydrogen difference is huge because
try and
here
solve it for you.
number of alpha hydrogen is 10 and 5, but here just losing one hyperconjugative structure, it can gain stability from his angle strain. So it can do
I
that.
hope this question should. This
Help
is the
you
last
to
problem. I am
solving
some
it for
upcoming
yourself.
assignments and
Just try
also
it by yourself and
whichever examination
I
you
will
are
solve it in the
preparing
next
for.
class. Okay. So
let's try to solve the first one. This bromide will get
thank you
removed from
everyone
the system.
for your attention. So I
As you
just
know,
give
this
a
is
recap.
methanol. This oxygen has lone pair. This is a weak nucleophile. This is not
Thank you so
strong
much. This is
nucleophile.
the
This is a
recap
weak nucleophile
where
because oxygen is not
I have
negatively
discussed
charged.
about SN2
If it is
reaction
not negative,
followed
that
by
is weak
some
nucleophile.
problems.
That weak nucleophile means is not
I
that
hope
much
this may
faster
help
it
you
will
to
attack.
solve
If
some
anything
unknown
is
problems
weak
in the
nucleophile, that will go
coming
through a
examination
SN1.
whichever you are
If the nucleophile
preparing
is
for.
strong, that it has
Then
negatively
I have
charged
discussed
or
about
something
the
like
energy
OH
diagram
minus
for
or OH
endo
minus,
and
that will go into
exothermic
a
reaction.
different type of reaction. But if the
Endo
nucleophile is
exothermic
not
reaction
charged,
and also
then you can get an idea that
for
it
SN2
will go
reaction.
through a SN1 type of mechanism. So if any reaction is
Then I discussed some problems where I gave this
any
to
reaction is in
try by
water
yourself.
or
I will
ethanol,
discuss this
that
in the next
usually
class.
goes through a
Then I
SN1
discussed
mechanism.
about elimination
Understood?
and
If the
difference
nucleophile
between
is not
substitution and
negatively
elimination.
charged, those
What is
reactions usually goes
elimination?
through a
Example
SN1 type
based
of
on that,
mechanism. So
followed by
if
U1
any reaction,
elimination,
they are not
E2 elimination
see
and
in
some
many
examples based
8
on
or
that.
8 question, they are not even giving
And at
the
last I have
nucleophile. They are
given
just
this
mentioning
problem to try it by yourself. I will
hydrolysis
solve
of
it
the
in the
reaction.
next class,
Hydrolysis
which will
means
be in the
the
same
reaction with
time
water.
on Sunday,
Or they are
4
saying
to 6.
the
I hope you guys will join and try to understand
methylation
as
of the
much as possible. I
not
will provide
methylation like
the slides
anything
and
like
recording
hydrolysis of the reaction. So the
to
reaction
the
is in water.
NPTEL
If
site,
the reaction is
and
in
I
water,
hope they have
that
provided
means
you
that
the
is not
access
negatively charged.
where you
Reaction
can
will
get
goes through a
the slides
SN1.
and the
If
questions.
you go
If
through
you
a
are
SN2,
forgotten
then
or
it will get
the
a
same,
wrong
you can
answer.
get that question from
Understood?
that place also.
Whenever this is hydrolysis
Thank you.
or water or
Have a
ethanol,
nice
that
day.
will goes through a SN1 type of
Thank you, ma'am.
Thank you so much.
So
Bye.
let's try to solve this one. So first bromide will remove from the system and we will get our carbocation. Now this carbocation
3 degree carbocation. This is the highest step. It has highest step because it has 3 3 1 7 alpha hydrogen. And so our product will be this one. And CH3OH, not OH, CH3OH. Now CH3OH means this part will add up and we will get oxygen will be positively charged because it's giving one proton, one electron. So now as it is oxygen is positively charged, so we take electron from this hydrogen bond, then H plus will get removed and we'll get this one as our product. So now let's go to our next question. What will happen? Here I have already shown the product. So here it is 4 member, but in the product we are getting 5 member. How is possible? So it's just first remove the lone pair, remove the leaving group. Whenever you are getting this type of system, just remove the leaving group first. Then we will get an idea. So we are forming this one. Now we all know that here why this is ring shifting is not happening in this place, because 5 member rings are stable. 5 and 6 member rings are stable rings. 5 and 6 member rings are stable rings. That we know. Because of that bond angle strain and all. The 5 and 6 member rings are stable. But 3 member rings are not stable. That's why this ring has prone to form a 5 member ring. If it has probability, if it has chance to change itself to a 5 member ring, because it's not stable, it's very fast to change to a 5 member ring. That's why. So, and it is a 2 degree. So this carbocation is not that much stable. Here it was 3 degree. So carbocation was already stable. Here the carbocation is 3 degree. So carbocation is not that much stable. So that's why this bond will shift to this position. Then it will be like carbon-carbon bond shifting. Carbon-carbon bond shift. So it will lead to this type of compound. So now the positive charge is this, because bond is shifting from this position. So this carbon is now vacant because we are taking electron from this carbon. So this carbon is now electron deficient. So positive charge here is a carbon. So the positive charge will move to this position. Now this carbocation is also 2 degree. So there is another chance, if there is any chance to get a stable carbocation which is 3 degree, it will go that way. So there is a hydrogen atom available. There is a hydrogen atom available. So it will shift this alpha hydrogen. So okay, what will happen? Alpha hydrogen shift. This shift is not hyperconjugation, it's shifting totally. This part of the bond is coming here to this position, it's shifting. So this bond will shift. This carbon hydrogen bond will get shift to this position, and we will get. So the carbocation, this positive charge, this center is electron deficient. So this center will be electron deficient. Understood? So this center will be electron deficient.
Now water is in the medium. Now this carbocation is 3 degree plus 5 members. 3 degree plus 5 members. So it is stable now. 3 degree plus 5 members. So it is stable, enough stable. So now this water will later and we will get our this. Understood? Any doubt? I think it's clear. So here is a bond shape. So whenever you, that's why it's very important to determine if the reaction is going through a SN1 or SN2, because in case of SN2 there is no chance of rearrangement because the carbocation is not forming, right? In case of SN2 the leaving group will just go from here and nucleophile will just enter here. So there is no chance of rearrangement in case of SN2, but in case of SN1 there is a chance of rearrangement, that carbocation will rearrange to form the more stable carbocation. So it's very important to determine our reaction is going through SN1 or SN2. So if there is any weak nucleophile, that is methanol or water or any uncharged solvent, that will be a SN1. And if the nucleophile is charged like OH minus or OMe minus or any charged nucleophile, that will be go through a SN2 pathway. Okay. So today's now is almost end to our class. So this is the last question of today. It came in GATE 2019. I added this question so that you can relate that all whatever we are learning by this class will benefit us to solve our gold examination, which is GATE or NET. All these type of questions come with very easy topic and it's just a one shot and you will get a right answer. So if you can get a right answer of this one, you are getting 1 mark in GATE. So try to solve this one. Amal answered, Rajan answered. Everyone is saying D. Okay, let's see. See, whatever you know, this is here. This is a Grignard compound. This is a Grignard compound. So in case of Grignard, this is negatively charged and magnesium is positively charged. So here the nucleophile is CH3 minus. Here the nucleophile is CH3 minus. So this one will attack to this position and this will open. So we will get CH3 and O minus. Now in medium they have given H plus. So it will take H plus or HCl means they are giving H plus. Like acid is giving H plus. Any acid they can even write as H plus. They can write even an acid H2SO4. Any acid is giving H plus. So this is what we are getting. Now as we are adding acid, we can't say our reaction that you will just take one proton. You can't take another proton. You can't control that. So if in medium you already have acid, it is very, because oxygen is there, so it will take another proton. You can't stop him that you can't take another proton, you have to take just one proton. You can't stop him.
So it will take another proton. By this oxygen lone pair, and this will be OH2 plus this oxygen is giving its own. So it's a very good living group, because water is a very good living group. We are getting water. That is, water is more stable thing, because around is everything is water. So water is the most stable thing. It will get removed, and we will get. Sorry, there is a hydrogen. So getting this. Now I have told already that 4-member rings are not stable. So if there is a chance of shifting, and this is a 2-degree carbocation. 2-degree carbocation has not that much stability. It is 2 degree and with a 4-member ring. So it's very prone to rearrangement. It's very prone to rearrangement. Because it has 2 degree, it has not that much stability in itself to control itself to not to get rearranged. So it's not that much stable, and moreover it contains a 4-member electron, a 4-member ring. So this body will shift from carbon center will shift here in this position. Now similarly there is a hydrogen like the previous one. So the hydrogen will shift and will form. This hydrogen will shift to this position and will form. So this hydrogen is shifting, so this center is now electron deficient. And when as H plus we have taken, so there is a Cl minus in the system. So this Cl minus will attack this positive center and get our product. So the answer will be D. So whoever has answered correctly, Rajan, Amol, Sri Vikram, Deepika, Logeshwari and Tejashwini, you can see that it is a 4-member ring. So 4-member ring is not that much stable. So that's why it's very prone to rearrange. Okay? Sorry. Okay. So this much for this class. Anyone has any doubt? Okay, I'll just give a short recap. We started with aromaticity. We have explained aromaticity of different type of compound and how we can prove that nitrogen lone pair is localized. Thank you, Rajan. Then I discussed about resonance, hyperconjugation, shown some example. Then SN1 mechanism and this question. So okay, I think everyone has understood and enjoyed this class. We'll meet in the next class in the next Sunday at the same time. So I will upload this video in YouTube and NPTEL also. I will upload the video already. I don't know how can I send the questions actually. I have to check with the NPTEL how to send these questions. But I will upload the video by NPTEL. You can go through the video and check the questions. And I will upload my slides also there. But how to send the question, I have to talk to the NPTEL. Then I will send this question to all you guys. Thank you everyone. Have a nice day. Enjoy your Sunday.
Bye.